So, chapter 20 is our last chapter dealing with thermodynamics and heat and its relation to energy and all of that sort of stuff. And essentially, there's going to be three things that are threaded through this chapter. It's all about the second law of thermodynamics. We did the zeroth, we did the first. The second tends to be, in some ways, obvious, but in other ways, a good bit more confusing. And one reason for this is because if you read any textbook, you will see multiple descriptions of the second law of thermodynamics that seem completely unrelated to each other. I guess part of it is that there are different ways of describing it, but also it's the type of thing that sort of touches a lot of different areas of physics. So we're going to do that as well. You can see here there's like this person's name and their statement of the second law. And we're going to do that multiple times because different ways have different ways of describing it that sort of touch on different interesting aspects of the second law of thermodynamics. Okay? Once we see them all, you'll kind of put it together and be like, oh, I kind of see how all those are hinting at the same idea. They're just looking at it from a different perspective. Okay? So the chapter as a whole is about the second law of thermodynamics, but it's going to break down into sort of two parts. The whole first half of the chapter, which is essentially what we're going to do today, deals with heat engines. Okay? We're going to look at a variety of aspects of that, look at some particular parts of it so you kind of get a feel for how they work, and look at some calculations. And then the whole second part of the chapter deals with the concept of entropy. So we're going to have heat engines, and then we're going to have entropy, and then that's basically going to be the end of all the thermodynamic stuff. Yay, is what I say. Okay? So, are you ready to sort of embark on this last little piece of thermodynamic stuff? I heard sure, just from a buried state there. I don't know if you could hear that. It's like, sure. That's all I got. Yeah, I'm with you. Let's move on to E&M, electricity and magnetism. Things get interesting there in a lot of different ways. So, second law of thermodynamics. Here's where we're coming from. The first law of thermodynamics, which we have an equation for that we've been using sort of over and over and over in different ways, is essentially a statement of conservation of energy. In other words, we can track where all of the energy goes, and we never get extra energy or lose any energy or create any or destroy any. Every little piece of energy is accounted for, okay? So we can look at a lot of different processes and be like, oh, energy is conserved. I can tell, like, I started with this much energy, and when I ended, I had the same amount, but maybe now some of it is in this form, and some of it is in another form, okay? The problem is, as you can see there at the top, there are many processes that we could observe and look at and say, oh, I can tell where all the energy is going. Energy is conserved, but yet we never naturally see that happen, okay? In other words, take a look at this example that they have with a broken cup. So someone has decided to break their mug for whatever reason, all right? I don't know why. Odd. This happened last night. Strange that this would come up today because we didn't set it up this way. My wife and I are sitting on the couch. And then all of a sudden it's like, okay, day's done, time to go to bed. And she like jumps up off the couch for whatever reason, but in the process goes from kind of like a reclining position to vertical and like kicks her feet out as she goes and kicks the table in front of us. A plate was on the table. It goes flying, and now it's shattered across the room, and now we're both awake. So, alas, we end up with a broken plate. By the way, it's still there. Because what do you say at that point? You're like, I'll deal with that tomorrow. Because you're not going to pick that up right before bed. And then second of all, it's like, I've been doing other stuff today. I still don't want to deal with it. So there's still just like broken plate everywhere. Just trying not to step on it and bleed is basically what we're trying to do at this point. So here's what doesn't happen, even though the first law of thermodynamics would still hold. Energy would still be conserved. You can imagine that even in its broken state on the floor, all the little pieces of mug or all the little pieces of plate that are there, we know that they have energy. They have a temperature, and we know that that corresponds to internal energy of all the molecules that are flying around. There's energy that's there. Well, why doesn't that energy just decide to restructure itself and still all be there and put the plate back together? You're like, well, because it just doesn't. Well, yeah, it just doesn't. But at the end of it, like if all the little pieces have a certain amount of internal energy, and now we put the plate together, All the little pieces are still there, and they have the internal energy. They're just like all together instead of all apart. The sum total of energy is still the same. Energy is still conserved, even if it were to just spontaneously put itself back together. Just like it was conserved when my wife kicked it and sent it flying across the room and it broke into a bunch of pieces. Okay? The second law of thermodynamics takes care of this. It basically gives us a direction in which things naturally or spontaneously occur. It's almost like we take the first law of thermodynamics and then add this little correction, because it's like, loophole. Things could go both ways in this equation, but we can't allow that because we observe the world and say there's one way that they go and there's another way that they never go unless we do the work. Okay? I'm going to have to pick that plate up. I'm not going to repair it. It's going to go in the trash. So I'm not going to do the work to put it together, but alas, I do have to go pick the thing up eventually. So it is a statement, the second law of thermodynamics, of what happens in nature and what doesn't. I should add a little word here. Let's say of what happens spontaneously, to be a little bit more specific, in nature and what doesn't. Because clearly, in nature, I could put the plate back together. That's a thing that could happen. It's what nature's not going to do on its own. So another way of thinking about this is in terms of all of this thermodynamics stuff that we've been talking about, in terms of heat. So Clausius, I guess might be how you say his name, said that the second law of thermodynamics says that heat flows, and we'll say spontaneously again, from things that are hot to things that are cold, but never the other way around. Now, we'll see later in this chapter there are things that I can do to make the heat flow the other way, but that always requires me putting some energy in. I have to do work to make that happen. If I just let nature do what nature is going to do, the heat will always flow in one direction from hot things to cold things. And I think we all know that that's what's going to happen. Okay, it's kind of an obvious thing. So it turns out that this whole idea, the second law of thermodynamics, was explored and discovered and sort of put together extensively when people started trying to use heat flow to get them to do work for them, to try to build an engine using this idea of, oh, look, things go from hot to cold. So essentially the whole first half of this chapter is, in a way, looking at the study of things that eventually led to someone formally expressing the second law of thermodynamics. So you can see there at the top, the heat engine, this concept, was very, very instrumental in development of the second law of thermodynamics. People weren't trying for that, I'm sure, when it started. They were just like, hey, I want things that'll do stuff for me, right? We want to create something that will do some work for me. And it turns out it led to some more theoretical discoveries that were unexpected. So what is a heat engine? A heat engine is any device that takes what we understand now to be thermal energy, or it's going to take a flow of heat and convert that into some mechanical energy or have it do some mechanical work. Any device that converts thermal energy into mechanical work. Take a look at this schematic diagram over on the right. Let's describe it first, and then I want to make a comparison to something that we're all a good bit more familiar with. So you'll notice there is something at the top that is at a high temperature. How high? Who cares at this point? It's at a higher temperature than what we have at the bottom, where there's something that has a region of lower temperature. So first of all, there is a difference in temperature that are in two spots in the engine, and they're held this way, okay? Well, we know from the second law of thermodynamics that heat naturally wants to flow that way. It wants to go from what's higher to lower. So I'm not doing anything there. I just need to establish two things that are at different temperatures, and nature takes care of that next part. It's like, well, heat's going to go from here to here. That's going to happen. When that happens, though, I can put a device sort of in the middle of that natural process and use it to get some energy out in another form and have it do mechanical work for me, okay? So this whole schematic thing feels a little theoretical. It's like, okay, I can imagine something hot, something cold, heat's flowing. What in the world would I do in the middle to make this flowing heat, which is invisible to me, I can't see it, make it make something move, make it do some work in some way, okay? Notice the way this is set up vertically should perhaps remind you of something else that's like entirely mechanical. What if I started drawing? I'm gonna show you some of my world famous artwork here now. Are you prepared? No, you're not prepared. By the way, did you see this horse on the board? Wow, I did not draw that. Not at all. I'm wondering if maybe all those vectors and forces were there, and then just someone came along in between classes and drew a horse that just sort of fit. I'm guessing someone else teaches who can draw better than I can. So here's what I'm going to do. This is blue on purpose. Okay, so and I'm going to draw little arrows at the bottom here. Oh, that's nice, don't you think? And then I'm going to kind of turn it around this way. Ooh. If you're thinking, he's drawing a horse, he just started with the mane. That's not what I'm doing. No. Mm-hmm. Uh-huh. And then maybe here at the bottom, I'm going to go, ooh. Mm. That's nice. I'm going to add a little bit more now. Are you ready? In a different color. What color should this be? Oh, let's go with gray. Ooh, eyes are opening. You're starting to maybe see something there somehow. Maybe a little bit. Maybe not. I understand. So just imagine, if you would, that that's a waterfall. Nobody went, because either you're like, I know what it is, that's pretty obvious, or you're like, nope. Nope, not a waterfall. So water naturally wants to fall from something that's a location that's physically higher than another position, okay? Two physical locations, two physical positions, one of which we would say is higher than the other. Well, if the water is at the top level and I give it a path through which to flow, it's naturally going to go to the lower level, all right? That is analogous to heat wanting to go from a hot region to a colder region. In the case of the water falling, I could take that, some sort of water wheel apparatus, and just put it in the way of the thing that's naturally happening. And just let the flow of water turn the water wheel. Now something mechanical is happening, all because the water's just naturally doing its thing, okay? At that point, I could go back a few centuries and maybe, I don't know, connect that to some kind of mechanical apparatus that, what did they use it for? Any thoughts? I don't know, maybe it like churns milk or something. Who in the world knows, all right? Or maybe we could go a little more modern and connect it to something that generates electricity, okay? And we could convert it to another form of energy. In any case, the falling of water, turning something mechanical, is analogous to having heat that falls, if you want to think about it that way. And in the middle, I put some kind of apparatus that does some mechanical work, okay? So clearly, we're not going to use a water wheel. We're going to have some other type of apparatus that's going to do that for us. Is everyone okay with that description so far? Okay? I kind of like the progression here. The water falling and the mechanical thing, that's something that's visible to us, right? You can imagine that in human development, like it would make sense to first make tools using physics with things we can physically see. It's like, water falling. The water will hit something and it will do something else, okay? We're using the exact same principle, but we're sort of moving into the microscopic realm, into things that we can't see, but all of our understanding and theories tells us is there. This thing that's invisible, heat, is flowing from one place to another, and I'm going to use that invisible flow to do something that I can see, all right? You might notice as we get later in the semester, as we get into electricity and magnetism, it's almost like we use similar principles again, but take a step into the even more invisible realm and still reuse the same ideas. A natural occurrence that we just sort of step in the way and let it do something for us, okay? So we need to add some equations to this and also set up some rules for what we're going to look at in this chapter. So we are going to specifically focus on engines that run in a cycle that repeats. In other words, we would like this to just sort of keep going over and over and over and over and over and over and over again and do something for us. We don't want to have something that's the equivalent of Instead of water flowing, it's like, oh, I think I'll just take a brick and drop it once and have it like do something, and then that's kind of the end of the game. Like, that's not much of an engine, okay? We want something that's continuous, something that can repeat over and over, all right? If this happens, we can say that the change in internal energy for the system is equal to 0 over an entire cycle. And we can say that because it returns to its starting point. Or let's say starting state. How's that? It goes right back to where it was at the start. So the overall change in internal energy of the system will be 0. Notice the second point. Mechanical energy can come from thermal energy only when heat is allowed to flow from a high temperature to a low temperature. We've already talked about that a good bit. And also you can see there at the bottom, a temperature difference is necessary, which we'll talk about in a little bit more detail in a minute. So if you just look at this diagram, we can set up sort of a conservation of energy principle just looking at what we have there. So we could say that we have some heat that's flowing from the hot region, from the high temperature region, and it's going to split into two parts, but still the sum of the different things it splits into has to add to what I started with. So you can see that it's going to be equal to the amount of work that I get out plus the amount of heat that leaves and flows into the low temperature region. Okay? If it helps, think about diverting a little bit of that waterfall in a way. Okay? So some of it goes into the work, some of it still flows out at the bottom and then repeats the cycle once again. Okay? So the amount of heat that leaves the top equals the work minus what comes out at the bottom. I should also tell you that we will often refer to these two temperatures as the operating temperatures of the engine. By the way, I have discovered a new color, and I think I like it. I don't know why. You're like, that's not a color, that's just gray. It's boring. I kind of like it. It almost feels like I'm writing with a pencil or something all of a sudden. It's like, it's not quite as, you don't care. I'm just going to shut up. So let's see. One other thing I should tell you here is that we have a new sign convention for engines. You want me to change to another color, don't you? You want it completely black? No? I'm going with this one. This one's more fun. We're going to say that QH and QL and W are all going to be positive. Instead of talking about when heat is flowing out or entering in being positive or negative like I had before, in the case of heat engines, all of these are just going to be considered positive. You want me to change colors again? I'm just going to completely ruin your notes today, just for my own entertainment. So a temperature difference is necessary. Let's talk a little bit about why this is true. First of all, a temperature difference allows net work to be done. And we'll see a little bit more clearly why this is true on the next slide when we actually look at an engine. It allows net work to be done. We can say that a different temperature means less work is done to, how to write this? Let's just write it like it is for now, and I'll explain later. To exhaust heat. Less work is done to exhaust the heat. In other words, to do this QL at the end, to put out QL, less work is done than to input QH. There's a difference in the two. You could also just think about this as, what if I had a waterfall? Well, that wasn't a waterfall. It was just like at the exact same level. It's like, hey, water, go from here to here. And the water says, no, I don't want to. There's no reason for me to do that. And it just sits there. Like, it makes sense that I need a different height to make water move. It makes sense that need a different temperature to make the heat flow and to get anything out of it at all, okay? And we'll see that in more detail on the next slide. So let's look at an actual engine. In this case, steam engines. And lest you think a steam engine is like kind of antiquated and not something we use anymore, okay? Well, often this process is used even in modern times. We just change the source of the thing that's making the steam to begin with. So in other words, instead of, you see this heat input here, instead of maybe, I don't know, taking a bunch of wood or something and burning it to make the water become steam, like even like a nuclear power plant, like it can use steam engines to turn steam turbines. It's just using a nuclear source of fuel instead of something that's more of a dirty fuel like steam or coal, or not steam, like coal or wood or something like that, okay? So the steam engine is still applicable today. It's not something that just makes trains go in the past, I guess you might say, okay? The steam engine. So let's take a look at what's happening here kind of one step at a time. Once again, you see there is a region of high temperature, so they've drawn this in such a way that matches the schematic from the previous slide. And there's a place down here of low temperature. So we know that, well, the heat would very much like to flow from here down to here. We have this apparatus in the middle that consists of, oh no, something we saw last chapter. We were hinting at this all along. A cylinder in which gas can flow, and it is pushing up against a piston if it were to expand. We then connect that piston that moves to sort of a wheel, so all of a sudden it's kind of like the water wheel. Once again, it's just one step removed from that. And as the piston goes back and forth, you can make this wheel turn. Now maybe that wheel is directly connected to the wheels on a train, if you wanted to go there. Or maybe it's connected to something else that allows us to generate electricity or some other form of energy, okay? So clearly, like, nothing is going to happen, first of all, if we don't have a high temperature and a low temperature. There's no reason for the steam that's being created by putting heat in and making it go through here. Nothing will happen unless it's like, oh, low temperature is over there. I think I'll flow that direction, okay? So you can imagine during the first stage of this, if this valve is open, the steam flows in and pushes the piston to the right. So it has to do some work on the piston, first of all. And then this turns this around, and it kind of gives it some momentum, is one way to think about it, such that it's going to go past the halfway point and begin to come around the other side, in which case it'll go the other way and begin compressing the gas, okay? When that happens, this is set up such that the bottom valve opens, and as the gas is compressed once again, it pushes heat out the bottom side, and then, well, the steam recondenses at the low temperature, and the whole process can start once again. So when we talk about a net work being done, well, first of all, during this expansion phase, work is being done on the piston, and then during the compression phase, the piston is doing work on the gas. The key is, during that second part, it takes less work to recompress the gas. If you think about it, it sort of makes sense. At that point, the gas is already at a lower temperature. It's less energetic. It's not going to be as hard to recompress it as it would be if it were at a higher temperature, okay? So there's less work being done during the compression phase and during the expansion phase, and that allows you to actually get something out, all right? So we can take this and maybe modernize it a little bit in the form of a turbine, and they are simply only showing sort of the middle part of this. And again, you've got steam that's coming in, it turns this wheel, and then it's cooler on the other side so that it takes less work to exhaust heat here than it did to put it in at the top. And then this is just more of a, well, I guess a simpler, cleaner design at this point, okay? Do you get a feel for how this heat engine thing is going to work? Yeah, it's really not terribly different than a waterfall on a water wheel. Yeah, it's just we're compressing and expanding a gas instead of dealing with water directly pushing on a wheel or a turbine. So let's take a look at this in a little more detail and talk about the efficiency. How much can you get out of a heat engine? And I think I need to change colors one more time. How about this one? Can you see this at all? Oh, it's darker there than it is here. This is what I'm seeing. It's quite a bit different. I don't want to use that one. Ooh. I think I'll just write with this the rest of the time. Why not? And it'd be like efficiency. No, we're not going to do that. Let's just back this whole train up. Back the whole train up. We were just talking about trains. That's ridiculous. Efficiency, E, the efficiency of a heat engine. We're going to use a really, really logical equation. Efficiency is really just a measurement of what percentage do I get out compared to what I put into the system. Or in other words, we could write the efficiency as the ratio of the work that's done by the engine over QH, which is the heat input. And this heat input, QH, that's going to come from some type of fuel that's burning. I have to use something, consume something to get this work to happen. So this will be sort of measured in fuel burned, consumed. How much work do I get out compared to how much energy or heat I put in? So we can rewrite this equation just a little bit. We can go back to the equation we had on the previous slide where we said that QH is equal to W plus QL. And let's solve that for work and plug it back into the efficiency equation. So work is equal to QH minus QL. And then let's go to this color and say we're going to put it in up there. Oh, man, none of these colors are as bright as they are on my screen. It's boring me. It's just terrible. So now we're going to take that equation and bring it down here. You all hate me, don't you? I understand. I hate me, too. I'm the worst. Yeah, I heard that. You're like, oh, that's sad. I don't hate me. I'm fine with me. I enjoy entertaining half of you and making the other half of you just cringe with a little bit of anger and disgust kind of all bubbling together. It's kind of fun. So QH minus QL over QH. So I can factor out, or we can look at this any way you want to. We could say that that's 1 minus QL over QH. And if we multiply that by 100, that will give me a percent. So if we don't know exactly how much work we're getting out, maybe I just know something about how much heat I'm putting in and how much heat is coming out the other side. We can use that, or we can use the heat input and the work either way to calculate the efficiency. So notice something about this particular equation. What would I have to do to get 100% efficiency? That is one way of looking at it, yeah. I'm not going to go there quite yet. We don't have temperatures that are here. What in the equation has to be 0 to get 100% efficiency? Yeah, we would have to have this top term, QL, would have to be equal to 0 for 100% efficiency. In other words, there would be no heat exhaust. But I have to have a heat exhaust because I need a difference in temperature, right? I have to have a high temperature and a low temperature in order for anything to happen naturally. Like, take a look at this diagram here at the bottom. High temperature, heat, and then just straight into work. There's no low temperature region. That's how it would look if QL was equal to 0 and we had 100% efficiency where all the heat I put in did work. Well, that can't happen simply because of how the heat engine works originally. You could say that there's no reason for this to happen. In other words, the heat isn't going to leave the high temperature region unless I give it a low temperature region. It has no desire to do that, okay? So in some sense, it just sort of circularly makes sense that I have to have a QL, so we're not going to get to 100% efficiency in any way. However, it does lead to some ideas where if we can simply lower QL to get better efficiency. So it's almost like just look at the equation and be like, here's what I need to do in order to get more out of my engine. I want less exhaust heat to be happening. But I can go ahead and look at the equation as well and the way heat engines work and just give up on the idea that I'm going to get 100% efficiency. This type of engine isn't going to give you that. Okay? Any thoughts or questions about any part of that before we move a little further? Anybody? Anything? Hey, there's a whole row back here for me. I should just enjoy it. That's nice. Why do I bother standing up for an hour and 20 minutes? This is delightful. Do you like sitting in seats the whole time? Oh, yeah, because then you can, 10 minutes in, fall asleep, yeah? This is the perfect place to just, Why is no one sitting in this row? This would be my first choice of row in which to sit, I guess is a way to say that. I could bring like a pillow, just kind of recline. Look, there's no one there. I can put my feet up and just enjoy. I'm not going to do that to you. That's terrible. This is good. I think next class what we're going to do, I'm going to sit here, and all of you have to stand up for the entire time. That'd be great. Of course, then I'll be like, sit down. I can't see. I need to see what I'm doing. All right, so the efficiency of a heat engine. I think I am going to enjoy this for at least a minute because this is kind of nice. So you'll notice there is another statement of the second law of thermodynamics there on the bottom right, the Kelvin-Planck statement. A device whose sole effect is to convert some heat completely into work. In other words, to have 100% efficiency is not possible according to the second law of thermodynamics. And you read that and you're like, oh, well, that's not what the first statement said at all, but they are sort of interrelated. We'll have to go further before we see that connection, perhaps. So that brings us to something known as the Carnot engine. The Carnot engine, which I can tell you already does not exist. This is an imaginary thing. So we could describe this as an idealized, non-existent engine. However, the idea of this, Carnot working through the details of this, was again a big part of establishing how the second law of thermodynamics works, what its restrictions on us were. An idealized, non-existent engine. I gotta say, just reading that description kind of makes me just want to stop, right? It's non-existent. Why should we even bother talking about it? It's completely theoretical. Here's the thing that you should take away from the Carnot engine. It is the best possible. So it's almost like on the previous slide we saw an equation for efficiency and we said 100% isn't possible. But actually in reality it's even worse than that. There is a maximum amount of efficiency that's possible for a given engine. And the Carnot engine is like the perfect engine. It's going to tell us what the maximum efficiency possible is. And it's something less than 100, okay? So we have to learn a few different things here before I actually, get all the way to the bottom here where we talk about the Carnot cycle. All right? Look at that. I'm on top of things today. I realized I'd sat down, and there's a pretty good chance when I did that, I knocked off the battery pack for the microphone. Okay, the other day, I just hopped up after sitting down, and everything went flying, and all was lost. But today, I caught myself. Look at that. I'm growing as a human being, I think. That's fantastic. So, two types of processes, the reversible process and the irreversible process. So notice a few different things here about a reversible process. This is a process that we could just flip it around. We can go either direction for this process, and it doesn't really change anything. We don't lose any amount of work, and we don't change how much heat goes in or out. We could do the process in either direction. To have a reversible process, we have to have sort of the idealized situation like we had in Chapter 19, where we're drawing all these PV diagrams, but we have to understand that they're like a set of equilibrium states. It's almost like it's happening really slowly. We have a pressure and a volume. We change it a little bit. We have a new pressure and volume. We change it a little bit. We have a new pressure and volume. So in other words, it is infinitely slow, which sounds terrible, right? Consisting of a set of equilibrium states. It's quasi-static. This reversible process idea, again, it's kind of like the ideal gas law. It's just not real. It's sort of like as good as it's going to be. A reversible process is non-existent. You might get the idea that the Carnot engine is probably considered a reversible process, and that's true. It is a non-existent case. An irreversible process, on the other hand, is sort of just everything that actually happens in the world. All real processes will be irreversible. In other words, if I run the engine in one direction, like through one cycle, it's not going to end up exactly where it started, and I'm going to lose something in the process. I can't just say, oh, let's just go backwards, and I'll be exactly where I started. That would be the equivalent of being like, drop the iPad, and then pick the pieces back up into my hand, and I reversed it. It's exactly like it started, right? Like, that's irreversible. Once it's dropped and broken, I can't just reverse that process and get back to the state that I started. All real processes are irreversible. Something changes in the process such that I can't just send it backwards. So in the case of an irreversible process, well, yay, it's not infinitely slow, so that's kind of good. We actually can see something happen. But also, all those intermediate states are not quasi-static. Like a process is going to happen, so different parts of the gas that's expanding and compressing will be at different pressures, so that we can't say the entire gas is actually at a given pressure and volume at any point. So I can't really plot these on a PV diagram. So what we're saying is that the difference between a reversible process and an irreversible process is kind of like back in Physics 7a, you did a bunch of problems with like projectiles. It was like, oh, take a ball, throw it at an angle through the air, and develop some sort of function for how far it's going to travel if it starts at a given angle, okay? When doing problems like that, more than likely, you said, let's just ignore air resistance. You didn't even worry about the fact that your thing is going to be thrown off just a little bit because it's going to be hitting air molecules in the air, and it's not going to go quite as far as expected by the equation. Well, the irreversible process would be like the real world when you have to do the full calculation and take everything into account to see exactly what's happening, including the air resistance. The reversible process is a good approximation that sort of helps you learn. It's almost like sort of a first-order approximation to lead to the real thing and actually derive the real equations, all right? So we're going to specifically look at a reversible cycle to help us understand the way these things work, and that reversible cycle is going to be the Carnot cycle. So we're going to have a substance, some type of gas or fluid, that's going to start at some initial equilibrium state, and we're going to pretend that it goes slowly through a bunch of other equilibrium states that can be plotted on a PV diagram, and then gets exactly right back to where it starts, and then it all happens again, okay? So we're literally saying that when it goes through one full cycle, it's exactly back at the exact same pressure and volume as it was before, and the exact same temperature, and I didn't really lose anything in the process. So a little bit imaginary. So a reversible cycle, and we're going to say that in this reversible cycle, the substance that we're looking at is an ideal gas. So just the whole description here sounds quite imaginary, don't you think? It's like, oh, I'm going to build a non-existent engine consisting of a non-existent cycle that's full of a non-existent gas. That's just sad all the way around. But we're doing this to sort of see the best an engine or a heat engine can possibly be. It's like if everything was absolutely perfect, how good could the engine be? The Carnot cycle. So the Carnot cycle consists of four processes. And these are processes we learned about in chapter 19. We should already understand what these mean a little bit. So we're going to start in this diagram at point A, and we're going to talk about this theoretically first, And then I'm going to show you an animation that kind of connects it back to what we had with the steam engine diagrams before, so you can kind of see what's happening physically during these processes. So the Carnot engine starts with an isothermal expansion. In the diagram here, that is going from point A to point B along that first top curve. You can see that as that happens, the pressure is going to go down as the volume goes up, which makes sense. It's an expansion. There should be more volume. This is going to happen at the higher temperature. It's isothermal, so it's staying at the hot temperature during this entire process. And as it stays at that high temperature, we're going to say the input heat is added. If you think through everything that's happening there, if the pressure is going down and the volume is increasing, well, if I just let the gas do what it wants to do, well, the temperature would drop, right? Less pressure, more volume. So what I'm having to do to maintain that high temperature is I'm having to put some heat in to account for the expansion, okay? So me putting heat into the system, into the ideal gas, is maintaining that higher temperature. Isothermal expansion, for starters. Everyone okay with that? You could recognize that on a graph now, maybe? Okay. The second one is an adiabatic expansion. So we're still expanding the gas. So we're going from B to C now. And you can see that from B to C, it drops down below the isotherm, which means it's dropping in temperature at this point. However, the pressure is continuing to drop. The volume is continuing to increase. Because it's adiabatic, at this point we could say that no more heat is added or lost during this process. And we go from the high temperature to the low temperature. So the temperature of the gas drops at this point. So it expands, then it expands some more. During the first part of the expansion, we're putting heat in. And then I like to think of like the second part of this from B to C. It's almost like carryover. It's like we kind of got it started, and now I'm going to stop like pushing on it with heat and sort of just let it keep expanding as much as it's going to. Okay, it's kind of one way to think about that. At this point, we're at a place to sort of start going back to where we were. So we're going to start with an isothermal compression as it goes from C to D. This will happen at TL. Now the gas is at the low temperature as QL is lost, or we could say exhausted. Oh, just the whole word exhausted is exhausting, don't you think? Like I just started writing it and then I said it and I was like, by the time I said, I was like, oh, I'm tired just saying the word exhausted. QL is lost. It's exhausted. So here we stay at the lower temperature. QL is going down. It's compressing. So we could say at this point the volume is now dropping and the pressure is increasing. We're going the opposite direction. And then finally, we take a step back up in temperature. Okay, as we continue to compress the gas, there's an adiabatic compression. So we could say, because it's adiabatic, Q is equal to 0. We're going to go from TL to TH. And if you think about what's happening there, I'm not doing anything other than compressing the gas. It makes sense that compressing it should raise its temperature once again. Okay, it's going to be more energetic in that space. And let me see if there's anything I wanted to add to that last part. Oh, we should also say pressure goes up and volume continues to go down. Remember, on a PV diagram, we can calculate work by looking at the area under the curve. So we can do the exact same thing here. It's just in one case, remember, we have positive work that's being done on the piston during the first phase, and then negative work is being done as we recompress the gas, okay? So what we could do is find the area under the expansion curve and the area under the compression curve, and the difference between those two should tell me how much net work I get out of the system. It turns out that is the area of this shaded region. That tells me how much net work is done by the engine. And again, it's just the subtraction of the two areas under the curves, the compression and expansion curves. So to try to pull this whole thing together a little bit, let's see. Let's hop over here. Ooh, Can I make it a little bigger? Not too big. All right. We're just going to play this and see if it gets us anywhere as it goes through the cycle. Notice, first of all, and I can't point now because I'm in a different app. See the little dot all the way at the top of the curve up near the highest pressure point? That dot is going to move through the 4 different processes that you can see in 4 different colors. So in red, first of all, it's going to fall down where you have the isothermal compression, and then green is the adiabatic compression, and then blue is the isothermal expansion, and then green, again, is the adiabatic compression, okay? So you can see the 4 different things as it works through that. And we're going to say that we have a piston. It's got an ideal gas in here. And once again, that's connected to a wheel that turns, okay? So you can kind of see how these 4 processes relate to the different parts of the curve. And sadly, I can't make it stop real easily or go slower, so I'm just going to let it play a couple of times. And you've also got a thermometer there that's helping you see what's happening with the temperature as well. Ooh. Let's just watch this for the next 30 minutes. It's mesmerizing. Whee! So I think of both of those adiabatic parts when we're not actively putting heat in or letting heat come out as sort of just the carryover of the wheel and the piston, right? No heat is being added or lost in those points, but we already have this motion, so you continue to get an expansion and compression just from sort of what you started by putting heat in or taking heat out, all right? I should just let that go while I talk the rest of the time. I just saw my battery level drop. That's a real pain. Anybody asleep yet? You're asleep? How'd you raise your hand? It's interesting. How long do you think you could look at that before you just dozed right off? Like maybe you want to take this home with you, and like if you have insomnia, you lie down at night and you're just like, and then you drop your screen on your face, and that would all be sad. I will send this link later in case you would like to examine that and learn a little further. All right, let's all wake up just a little bit more. So, what can we say about the efficiency? Remember, we said that the Carnot engine is the best you can get, okay? So we can write out an equation for the efficiency of a Carnot engine, and then we can always look at a given engine that we have and say, well, if it were Carnot, this would be the maximum it could possibly be. And then we could actually calculate what the efficiency we're getting is and see how well we're doing compared to the best that's possible. So let's see. Let's write an equation, first of all, for the Carnot efficiency. And I'm not going to derive this or anything. E is equal to 1 minus TL over TH. So it's in terms of your 2 operating temperatures. These need to be in Kelvin for this to work. As they should be, because Kelvin is best. E is equal to 1 minus TL over TH. So it's only dependent on the operating temperatures. So notice this leads to what we see below, known as the Carnot theorem. All reversible, read imaginary, engines operating between a given 2 constant temperatures are going to have the same efficiency. And any irreversible engine, read real, that actually happens, is going to have some efficiency less than what you calculate here, okay? This is the maximum possible. A real engine is going to have some value that's less than this. So, take a look at this problem and maybe do a quick calculation. Notice they give you the operating temperatures. They also tell you the heat input and the heat exhaust. And based on our efficiency equations, you should be able to tell whether this is a perfect or Carnot engine, whether it's a real or irreversible engine, or whether maybe someone's making something up and they're saying they're getting an efficiency that's higher than the Carnot limit. And you can do the calculations and see. Don't you just hate none of the above? Like, what are the other options here? It's either fake, or it's real, or it's ideal. I'll give you a second to do the calculation and see what you come up with. Yeah. You're going to need both, actually. Going to have to do both. Who's got answers? Your sticker says Chronic Tacos.
Yes.
Whew, I like the sound of that all around. Where is Chronic Tacos located?
Newport Beach, California.
So not here. It's a bummer. Tacos are the best. They must be really good, though, if you're going to put a sticker on your laptop. Like, ridiculously good.
I mean, it's not.
You just liked the sticker.
I also like the tacos.
Okay.
I have low standards.
Low standards for tacos. Well, I don't know why we're talking then. I should just move on. So what'd you get? I don't have these numbers. Tell me what you get for this efficiency at the top. This would be the Carnot efficiency for this particular engine. Anybody? Help. Something more than 50%? So let's just say this is greater than 50%. And what do you get for the bottom one? I heard blah, 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 blah. Huh? 50%? Okay. Well, there we go. It looks like you're within the Carnot efficiency. So this is an engine that could actually exist. So it is an irreversible heat engine. It's something that's real. Okay? It's not none of the above. It's not a hoax. So just compare the two efficiencies, and you can see whether it's something that could possibly happen. All right? Before we leave the idea of heat engines, we should say that you can flip heat engines in reverse and get them to work for you in a different way. So maybe it turns out that I don't really want to take the natural flow of heat and get it to do some work, but rather, I have some work available. Like maybe I want to put something in and make the heat go where I want it to go. Make it go against its natural flow, okay? So in other words, we could do something like what you see over on the right. Notice this work arrow has been reversed. So in this particular case, what we can do is do some work on the gas ourselves, and now we get heat that's coming out of the low temperature region and going into the high temperature region, all right? This is in essence how we get wonderful, wonderful things like refrigerators and air conditioners. They are simply a heat engine that's being operated in reverse. So we could use something like an electric motor to put the work in and make the heat flow in a way that's against its natural tendency. Okay, so let's see. What do we want to say about this? So first of all, we can go back to the Clausius statement of the second law. No work, just having it naturally flow from cold to hot. Well, that's just another way of saying that it naturally flows from hot to cold, right? Looking at this in reverse, this is another version of Clausius' statement of the second law of thermodynamics. It's not possible to have a perfect refrigerator that'll just operate on its own. So let's see. We have a couple of other equations I want to give you with this. We're not going to talk about it in great detail because we did all the detail talking about the heat engine. Just keep in mind the exact opposite is happening now. The heat is flowing from cold to hot, which allows you to create a colder region and exhaust heat to some place that's warmer. So we've got something known as the coefficient of performance. And this is essentially an efficiency for a refrigerator or air conditioner or a reverse heat engine. And this is equal to Q, which is the amount of heat removed, over W, the work that's needed. And if you think about it, that just makes logical sense. Like compared to how much effort or work I have to do, how much energy I have to put in, how much heat am I able to move? It's never going to be 100%. There's always going to be some losses that are involved. So once again, we can rewrite this using the equation we had many slides ago, where QH is equal to W plus QL. And we'll rearrange that for work and plug it into the equation. So work is equal to QH minus QL. We're going to put that in there. So heat removed, that is QL, we could say. Let me put an extra subscript on that. Over QH minus QL. And we have an alternate form of the coefficient of performance. And I think that's about all I want to say about refrigerators and air conditioners. It's just a heat engine in reverse. You might sometimes see the term heat pump, which is a little bit odd in a way, but maybe if you have a house often, it's like, oh, does it have a heat pump? Well, a heat pump is really just a heat engine that's reversible, that works in both directions. You can make it pump the heat one way or pump the heat the other way so that you can heat the house, or you can cool the house, just depending on which way I decide to operate the heat engine. I like this diagram because, first of all, it's almost like this is what they decided is like the perfect outside stuff. You have to have a snowman and a shovel and a bunch of snow. And the perfect indoor world is just a nice, comfortable chair. Yeah, and apparently heat pumps are massive compared to the chair and the snowman. So, I don't know. It's a little bit odd. I don't think there's anything else we need to add to that, though. Okay? That is the end of heat engine stuff. Does anybody have any questions, comments, thoughts? Yes. Why would, okay, out of all the possible curves, right, we could just like make a box and have it go around. That's a good question. I don't know. I haven't thought about that. I'll leave you to explore or ask somebody else. Yeah, I don't have a good idea. I can see how the Carnot cycle matches to something physical where I can have an expansion and compression of gas, but I agree with you. There's a lot of other loops we could draw on a PV diagram. How we would create those in the real world, that might be a harder question. Second law of thermodynamics, heat engines and reverse heat engines, gets us most of the way through chapter 20. I am going to introduce entropy. We're going to do 2 slides, and then we're going to call it quits for today, and we'll pick up the rest of this chapter on Tuesday. Okay? I need to just get us started on this back half of the chapter. So, entropy. Entropy is also related to the second law of thermodynamics. We'll see that all the way at the end of the chapter, how it connects. Notice the description or definition of entropy. It is a measure of the amount of order or disorder in a system. A measurement of the amount of order or disorder in a system. We are going to use S for entropy. And we'll specifically talk about the change in entropy often. Did the amount of order or disorder increase or decrease? Which way did it go? And it is equal to Q over T as long as I have a constant temperature. This is a constant temperature in Kelvin. And Q is the amount of heat added to the system. And specifically, this is going to be for a reversible process. I don't know what I wrote there. Can you see that word? Reverable, it looks like. Did I write reversible? Is that actually an S? Wow, when you zoom in on handwriting, it really is terrible, isn't it? Like, it almost looks like something out here, but like we go in here and it's like, what happened? Oh, that's not good. So I need to fix my reversible. It's like, yeah. No, I need it. No, that's reversible. I just can't write. I'm sorry, everybody. Let's just fix this. Reversible. How's that? Who knows if I spelled it correctly? I'm lost at this point. The amount of heat divided by the temperature. So we could re-express this as a differential that we can integrate if the temperature is not constant. So T not constant. We could write this as ds equals dq over T, and then in order to find the change, not the change in temperature, but the change in entropy, we would just integrate that. And this would be from some state A to some state B, and we'll see what those look like when we actually do some entropy calculations a little bit later. So a few things here at the bottom we should point out. First of all, as I already said, we're always going to be looking not so much at how much entropy a current system has, but rather how much it changes as it goes from one state to another. That's going to be the thing that we typically calculate. We also need to point out that it's only dependent on where you start and where you finish. Unlike when we were calculating work in processes, how you got from point A to point B also mattered. When we're dealing with entropy, the process doesn't matter at all. The path that you take doesn't matter. It's just about the state you're in at the beginning and the state that you end with. And also, entropy adds to our list of state variables. It describes what condition the system is currently in. So the system has a pressure, a volume, a temperature, an internal energy, a number of moles, how much is there, and also an amount of disorder that's inherently in the system at a given point in time. So entropy is also one of our state variables. All right, so thermodynamics. Here's where we left off. I had just introduced the concept of entropy, which on the surface is kind of a simple idea. It's just a measure of how much disorder is in a system, which on its surface you're like, oh, I kind of get it. But practically what it actually means in calculations is a little bit more esoteric. So we're going to do a couple of examples here in a minute to give you a feel for how these problems work. And then we're going to extend the idea of entropy back into the second law of thermodynamics and sort of pull everything together in a way. So there's a couple of things I'd like to add to this slide before we leave it. First of all, we had arrived at this equation, which is the equation we're going to use for entropy in all cases. What I didn't add to this is that this is specifically, didn't I have trouble with that word on Tuesday? Or Thursday it was. I feel like I did. This is specifically for reversible processes. Reversible processes, they can go either way, and really you end up with the same results. Specifically for reversible processes. However, there's a nice thing about calculating the change in entropy such that this equation's insistence on being about reversible processes doesn't really matter. It turns out when calculating the change in entropy, unlike when dealing with work and the work done by a gas before, your starting and final states matter, but how you get from point A to point B doesn't matter. So you remember before when we were calculating work on a PV diagram, we could start at point A and try to get to point B, and we'd calculate a different work if we went this path versus we calculated going that path, okay? So different ways of getting from point A to point B through different states mattered. It turns out when calculating entropy, it doesn't matter. So we could put another little point down here. When we're dealing with real processes, processes where there are losses, processes that are not reversible, instead they're irreversible, well, we can just find a reversible process that still connects the same 2 points, do the calculation, and the same change in entropy will apply. So let's put a little note down here. We just need to find a reversible process connecting the same two states. Okay? Which allows us to use this for any real-world process. One other thing I should put down here at the bottom, just notice that entropy is another one of our state variables. It describes the system itself, much like pressure and volume and number of moles and all of that type of stuff. It's not like work and heat, which describes something entering or leaving the system that you're looking at. Okay, entropy is a state variable. So, our first example, we're going to start with an easier one just so you can get a feel for how this works, and then we'll do something a little bit more complicated that involves a real-world process. So, as long as you are dealing with a system that has a small change in temperature, it's okay to just use an average temperature, and it's going to give you a really good approximate result and allow you to get close to seeing what you need to. So notice in this particular problem, entropy change when mixing water. 50 kilograms of water at 20 degrees Celsius mixed with 50 kilograms of water at 24 degrees Celsius. All right, so let's draw water first of all. There's some water. How about that? And here's some more water. And I'm going to mix these waters together. And then we're going to have, well, double the water. What's the final temperature of this water going to be? Yeah, it has to end at 22 because, well, we have the same amount and it's the same substance, so nothing terribly difficult there. So let's say the one on the right is going from 24 degrees Celsius to 22, and the one on the left is warming up from 20 degrees Celsius to 22. We can calculate the amount of heat, first of all, that's being transferred. And we know it's going from hot to cold, so the colder water is going to be receiving the amount of heat that's being given up by the warmer water. And we have MC delta T for that calculation, which is going to be 50 kilograms times 4186, which is the specific heat of water, times a 2-degree temperature change from initial to final, from 24 to 22. So we're going to get 4.186 times 10 to the 5th joules, which is coming out of the hot water and into the cold, resulting in this final equilibrium temperature. So it's this amount of heat which is negative for the hot water and positive for the cold water. Okay? Once we have this, we can use our entropy equation, and we're going to say that the total change in entropy for this particular case is going to be the change in entropy for the hot water plus the change in entropy for the cold water. And the way we're going to do this is with some average temperatures. So I'm going to start by calculating this one. In the case of the hot water going to the intermediate temperature, we're going between 24 and 22 degrees Celsius, so we could say that our average temperature here, T average, is 23 degrees Celsius, or 296 Kelvin, roughly. And our average temperature over here is 21 degrees Celsius, or 294 Kelvin. So you're looking at the average temperature for that particular change in entropy, for that process. Good so far, right? Nothing terribly difficult there, I don't think. So we can take this down a little further and say that the change in entropy for the hot water, it's losing heat, so it's minus 4.186 times 10 to the 5th over 296 Kelvin. And the temperature in the equation we're using has to be absolute temperature, otherwise things aren't going to work out. Plus 4.186 times 10 to the 5th, and it's positive this time because the cold water is receiving heat, and its average temperature is 294 Kelvin. And once we punch all that in, you're going to get a small change in entropy. And we should change this to roughly equals because we're using average temperature. So you're going to get about 10 joules per Kelvin, which you'll notice is positive. It's an increase in entropy. There's more disorder at the end than what we started with. Another way of thinking about this is that, well, we had order in that we had two blocks of water, if you want to think about it that way, that were at different temperatures. If I have reservoirs of different temperatures, I can get work out of that. I can create a heat engine potentially. There's order there that will allow me to do something. Once everything has mixed to 22 degrees Celsius, there's a little bit less order. I can no longer do anything to extract work from this. I can't create a heat engine. And that's reflected by an overall positive change in entropy. There's an increase in disorder. Okay? I'm going to add a slide here and sort of generalize this process. All right? So you can use it for any case without having to sort of step through those details. So let me put another page here below. Whoops. I hear muttering as if there's something else there you were wanting to look at. A couple of people are writing. Questions, first of all? Anything there that's bothering you? Yeah? Throughout this class, we're going to look at it several different ways. It's a little vague, I understand. So in this particular case, think of two different temperatures as more ordered than just one temperature. Okay, so things are a little more disordered. You'll get a couple of more cases of that as we go through the day. All right? So in general, let's see. We need a new color. How about this one? In general, we can say, first of all, that heat flows in the direction we know. We could say from the hotter temperature over to the colder temperature. And we could say that it reaches some intermediate temperature. And we'll give that Tm, let's say. Heat flows from hot to cold, and it's going to arrive at some intermediate temperature, the entire system. So we could say that, first of all, we have QH, which is going to be a negative value because heat is leaving QH, is going to be equal to QC, which is my positive value because it's receiving heat. Heat is going into that substance. And again, that's essentially just from calorimetry. So we could write out the change in entropy, just like before, as the change in entropy for the hot plus the change in entropy for the cold. Or for the hot one, we have a negative value for the Q. And it's going to reach, we'll say, the hot intermediate temperature. We'll call that THM. Plus a positive Q over TCM, the cold intermediate temperature. And then we can rearrange that a little bit. So let's write that as Q over TCM minus Q over THM. And then we'll factor out the Q. Oops. I like that. Change in zero. What does that mean? I have no idea. I'm just writing random things now. Change in entropy is going to be Q times 1 over TCM minus 1 over THM. Yeah. Between the overall intermediate temperature and the temperature that the hot object started with. So in other words, in this particular case, it was 23. It went from 24 to 22. Okay? You could also think of it as the average temperature for the hot object's transition. Yeah. It's because in this particular case, we're calculating using average temperatures. We're getting an approximate result for the change in entropy. We can add one thing to this. We always know that THM is going to be greater than TCM, right? Just think of the last problem. The average or intermediate temperature for the hot object always has to be greater than that for the cold object. So we know from this particular equation that the change in entropy in all of these cases is going to be positive, which is exactly what I would expect. Okay? That second term is going to be smaller than the first term, and we're going to get a change in entropy that's positive every time. Everything's toward increasing disorder. Which, first of all, just saying increasing disorder, it sounds sad, right? It just feels a little sad. It feels like my life in general. We have determined, my wife and I, that I am like, just the area around me experiences more change in entropy than other areas. Like there's more increasing disorder around me, such that the net increase in disorder between me and my wife is still positive, but like she kind of counteracts it a little bit. But around me, the increase in disorder is kind of ridiculously high. It's way more positive than it should be. I'm a local anomaly, you might say. I don't know. So a change in entropy is always positive. So this is going to lead to some extra depressing results as we continue through the end of this chapter. Let's do one more calculation. And in this particular case, we're going to look at a real process. In other words, a process that's irreversible. And we're going to do that by trying to find another process between the same two states and do the calculation using the integral this time. So notice, we're looking in this case at a free expansion. Remember, this is an adiabatic process where we essentially have some gas that's bottled up in one volume, and then we just open the chamber and give the gas more space and let it expand or sort of diffuse into the other space however it wants to. It doesn't do any work, and no heat is exchanged with the surroundings, okay? Once I do that, there's really no way for me to reverse the process. This would be almost like, I don't know, if we put a big barrier down the middle of the room and evacuated all the air from one half of the room, made it a vacuum, and we had all the air trapped in the other side, and we decided to just open a door in the middle. And then we waited a while, and we can imagine gas particles would enter the other room. And then what are we going to do now? Like, if we want to put them all back in the box, I would have to do work. Like, there's no way for me to get the original process back again. Yeah. Very slowly? I guess you could, but perhaps not practical. Okay? Adiabatic free expansion. So let's list a few things that we know about an adiabatic free expansion. So first of all, Q is 0. Okay, that's just the definition of adiabatic. For free expansion, the work that's done is 0. Very quickly, this is going to seem a little bit pointless. We know that there's no change in internal energy, so that's 0. And based on that, we also know that there's no change in temperature. Everything's 0 in this particular case. So we could say that T1 equals T2 equals a constant temperature in this particular case. This is an irreversible process. But all we need to do is look at the same starting state and ending state. Notice it says that we have the case where it's going from volume 1 to volume 2, and volume 2 is larger. It's expanding. We just need to find something that matches these conditions again and just use what we know about that particular process instead. So notice, if the temperature is not changing, that might lead you to think of an isothermal process. An isothermal process, because in an isothermal process, well, these things are also true. Okay, so it's another process from point A to point B that happens to be something we know how to handle. It's a reversible process that we understand. So let's write a few different things down. First of all, in this particular case, we can say that the change in internal energy, which is equal to Q minus W according to the first law of thermodynamics, is equal to 0. So Q is equal to W. And we can also write down dQ is equal to dW based on that, which is equal to pdV. So notice we're going back to something we had before in chapter 19, in the last chapter, a calculation of work. We know how to do that, and it also happens to be equal to a calculation of heat in this case. So we can say that the change in entropy for the gas is equal to the integral of dq over T. And then we're going to substitute that in, this PdV. So I need to get it to the dq. I'm going to go around this way. You're thinking, why? I don't know. Yeah, that was pointless in every way. There we go. We'll plug it in there. Yeah, I know there's like 3 of you who are like, oh, we got to follow the exact same path. The path doesn't matter in this case, remember? Yeah, I know. That was dumb. So this is the integral of P dV over T. And since the temperature is a constant, we can pull that out. And let's put some limits on this integration. We're going from V1 to V2 as expressed up in the problem. And then we can use the ideal gas law to substitute N for P, which is something we did before, V1 over V2. So that's going to be nRT over V dV. I've apparently decided to stick with this pink color. Why not? So let's see. The T's cancel out. That's kind of nice. And NR is a constant. So now I just have the integral dV over V from V1 to V2. Which gives us NR times the natural log of V2 over V1. And you could use the numbers given up in the problem to calculate the change in entropy for this particular gas. It applies to the isothermal process between V1 and V2, and it also applies to the free expansion between V1 and V2. So dealing with an entropy calculation doesn't necessarily involve something new. It involves doing the same calculations you did before. It's just now we get to apply them to the dq that lives inside the entropy equation. Okay? That, I think, is all I want to show you with regards to the calculation. Any thoughts, questions, complaints? How's the caffeine level? You look about the same. It's not working. Give her another dose. You got another dose? More. Nah, like triple it, I think. Oh, it tasted bad? And you know what that tastes like? Sounds kind of disgusting. Yeah, I would agree. No cotton candy today. When was the cotton candy day? Did you try some of the cotton candy that they were giving out that they'd left there for hours? No? Okay. All right, so let's relate entropy back to the second law of thermodynamics. And I noticed a missing letter here. This should be isolated system. The entropy of an isolated system never decreases. It's always going to increase. The best case you can get is that the isolated system might have a constant amount of entropy in the case of reversible processes, but in all cases of real-world processes where we're not dealing with the idealized case, well, it's going to increase. It's always going to go up, which leads us to another statement of the second law of thermodynamics. I think that this is the third one now, maybe. Looking back in your notes, I think this is the third one. So since we're dealing with irreversible processes everywhere in the real world, we can say that the total, wow, another misspelling, look at this. The total entropy, apparently I was just typing too fast. Either that or I, just slightly misspelled entropy and got autocorrected to energy, who knows. The total entropy of any system and its environment is going to increase. The total entropy is going to increase. So we could write something that looks like this. We could say that the change in entropy equals the change in entropy of our system plus the change in entropy of our environment, and that's going to always be equal to 0. The change in entropy of our system plus the change in entropy of the environment is going to be greater than 0. It's going to be positive. So this means that if I look at everything, it might be possible to have some local decrease in entropy. Maybe I have some small, very specialized system where entropy is dropping. But if that's true, then there is some other place in the environment where there's a greater increase in entropy to keep the overall change as net positive. Okay? It turns out that when I look at all of the physics laws that we study, typically we have conservation principles. At this point, we've dealt with like conservation of energy and conservation of momentum last semester. We are going to look at conservation of electric charge a little bit later on. Typically, we talk about things that stay the same. If it increases somewhere, it has to go down in another place. We can track everything. Entropy is a little weird because it's an inequality. It says that it's always going to be positive. It's always going to be an increase. So we don't have a conservation law. Instead, and we don't have an equality, we have this inequality, which sort of stands alone in physics. It's one of the only things that exists that happens that way. So what this is doing, remember all the way back to the start of this chapter, if I were to scroll all the way back to the first slide, we said that the second law takes care of this problem where I could have conservation of energy in processes that don't naturally occur. It gives us sort of a correction and tells us the way that processes naturally go. Now we have that correction. At this point, we can say that natural processes will go towards increasing entropy. The energy is conserved, and it's conserved in such a direction that entropy is going to increase. And sometimes, real processes are, we could say real and ideal processes are almost like going back and talking about gravity and projectiles. Like the ideal process might be ignoring air resistance, while in the real world we know there's friction and drag and other things that we kind of leave out. That's the way I would think of the difference. Okay? The world is just full of real processes. Things that really happen that are irreversible and that tend to leak away some energy. So when I'm talking about increasing entropy, the second law sometimes is given this nickname, times arrow, which seems a little extra dramatic, I think, in a way, right? What we're trying to say is that if you were to look at a film and try to determine, like, which way is forwards and which way is backwards in the real world, you could look at it and say, well, like, I know this way things are breaking and staying broken, entropy is increasing, and if I play the film the other way, things are being put together and entropy is decreasing. Well, you can tell which way is the proper direction of time based on this increase in entropy. So, let's look at the last slide in this deck, and then we've got a few in 20B that we're going to talk about, and then we're going to be done with thermodynamics. So natural processes we have determined tend toward greater disorder. I just want to point out that this is not just about thermodynamics. Even though we call it the second law of thermodynamics, this principle sort of applies outside of that realm into the universe at large. For instance, if we were to have, and maybe this will help with the understanding of what's meant by order and disorder, maybe I have like, a canister that has salt in it, okay? I have a salt shaker. And for whatever reason, I decide to put pepper in with the salt in the same shaker. I don't know anybody that does that because typically you want different amounts of salt and pepper. That'd be a little odd, right? And let's say that on top of that, you've decided, sometimes I want salt and sometimes I want pepper. So I'm going to put in a layer of salt and a layer of pepper and a layer of salt and a layer of pepper and a layer of salt. So it's kind of like one day you get salt, the next day you get pepper. One day, the next day you get salt, and then you get pepper. You only get one or the other, all right? You could think of that system of salt and pepper all in layers as a system of order. It's not a terribly useful type of order, but it's still order. It took some effort, it took some work to put things in that configuration. If I then just decide, well, first of all, if the particles are roughly the same size of the salt and pepper, and I just start shaking it, okay, eventually you can imagine the salt and the pepper are going to mix, and then maybe I have my salt-pepper seasoning or whatever that's maybe something a little bit more useful, okay? I can't continue that process and be like, oh, it's all mixed up, now you shake it and put it back together. Okay, fine. You shake the salt and pepper thing. It's not like once it's mixed, it's going to like unmix itself and go back to the original layers that are there. So that's a case where there's not really any thermodynamics involved. It's just like collisions between particles and somebody doing mechanical work, right? There's no thermodynamics. Still, in that system, things tend toward disorder. We talked about at the start of the chapter the broken coffee mug, or in my case, the plate that my wife kicked onto the floor that went sort of everywhere, right? That thing didn't fix itself. I waited for a couple of days. Yeah, it just stayed there. Eventually, my wife's like, I'm getting glass in my feet. I was like, okay, I think I'll pick it up. Maybe I was trying to see if it would repair itself at some point and put itself back on the table. Never happened. I was a little bit sad. So I picked up the pieces of glass and ceramic and whatever was there. It didn't put itself back together. If we were to go back and talk about the problem we had a few slides ago where we had hot water and colder water, right? Actually, both of them were relatively cool, or room temperature-ish, right? There's no way for me to put those things back together and then just sit back and wait and eventually hope that maybe the hot water will go to one side and the cold water will go to the other side. That doesn't happen. That's more of a thermodynamics process. I saw a question over here. Non-zero probability, yes, which we're going to look at in a minute. I would agree. There is some non-zero probability, but you're going to be shaking for a while to perhaps bump into that option. If that's the case, it increased somewhere else more. It's hard to say, because first of all, you had to shake the thing a long time. What else increased in entropy? What's that? Maybe the entropy in your arm increased because you died. I don't know at that point. Hypothetical, yeah. That's in the case of a system that's isolated, so we're not looking at the environment as well. Each individual part, you might think of the whole system as being isolated, but each part of it wasn't isolated. We had a mixing that was happening. So it could be constant. Constant's like the best case scenario. More than likely it would increase. So it's either constant or increasing. It's not necessarily constant in all reversible isolated systems. Anyone else? Before we get to the end of this slide, which is extra depressing. More randomized motion. More randomized is kind of an odd thing to think about. Tends toward random motion and more random locations. Yeah. So you're saying maybe the entropy should be balanced out there? It's a good question. The only thing I can say is that at that intermediate temperature, there's more overall disorder than there is at those two separated temperatures. What that looks like microscopically, I can't really speculate. Yeah, I don't have a good answer for that. Yeah, I'm sorry. It's a good question. Good question. Let's see. What else should we say about this before we get to that last line that everyone's looking at down there, which just looks depressing in every way? Yeah, you see it. Let's see. So a couple of different things. First of all, we can just say that overall, no matter what happens, some energy is becoming less useful. So keep in mind that energy is still conserved in all processes. We can keep track of where it all goes. It can't be created. It can't be destroyed. The thing is that some of the energy now I can't really get back and do something with it. Much like right now, I'm burning energy. I ate food for lunch. I'm talking. I'm standing. I'm burning energy. But when I say burning energy, I'm not burning it in a way that it's now gone. It's just I'm converting it to other forms. And we understand that that's what we mean by conservation of energy. Maybe I'm heating up the air just a little bit by vibrating the air molecules nearby. Maybe I'm rubbing against the floor a little bit with my shoes, and there's a little bit of noise. There's a little bit of this, that, and the other. other forms of energy are being created, but that energy is now not useful to me, right? It's still out there in the world. Like, all of you absorbed a little bit of my energy. Thank you for that. And now it's not useful to you. It's not useful for me. There's no way for me to just like reverse the process, right? Take it all back and then walk out of here with the exact same amount of energy that I entered with. There's no way to do that, although it would be awesome, right? It'd be fantastic. So we could say that it's less useful, or in other words, energy gets degraded as we use it. It becomes less useful to us. There's no way for me to extract work out of it as it becomes degraded. Much like we said with that previous slide, I started with 2 temperatures. I could make a heat engine. When it's done and I mix them together, we have 1 temperature. What do I do now? I can't extract anything by creating a heat engine at that point, okay? So this is where this whole theory of eventually all these processes might complete themselves, and we end up with what's called the heat death of the universe. I'm sad now, right? Where at this point, everything has reached 1 temperature, an equilibrium temperature. There are no differences in temperature anymore. Everything has just stabilized, and now there's no way to extract work in any way out of the universe. And then we're just done. Okay? This is completely theoretical. It seems to be like an extrapolation of what we see with small processes everywhere around us. But there's, of course, arguments based on like, well, should I really apply something like thermodynamic principles to something that's as big as the universe itself? Is that valid? Does it make sense? And you can probably go upstairs in this building and find people who are working with the theoretical limits of that. It's beyond or above my pay grade. So, alas, I won't speculate any further. Just keep in mind that's like the extrapolated limit of this whole thing, and it sounds a little sad. So, a little bit more about disorder. The way that we interpret all of this statistically with something that's a little bit more practical, something we can see, something we can understand a little bit better. So you can see there at the top, microstates and macrostates. This harkens back to the beginning of our discussion of thermodynamics, where we talked about the microscopic system. In this particular case, imagine we're looking at a gas and we're trying to determine what every molecule is doing, where it's located, and what its velocity is, which direction it's traveling and how much. I can't really know that. So we can't know this. And one might say, well, we can't know this now. Well, I would agree with that. Who in the world knows what technologies may exist in the future? And I watch Star Trek. Yeah, Star Trek, like they have a transporter. How are you going to transport matter without knowing the microstate of every molecule in that matter? All of a sudden, it's like that becomes incredibly science fiction the more you think about it. The computer processes and the analysis needed to analyze every particle in the human body and then reproduce it somewhere else, yeah, that starts to sound scary. I read a book once called The Physics of Star Trek. It was depressing in every way, because it's like, yay, Star Trek book, like science fiction, bring it on. And then like actually connecting it to the real world and thinking about the physics implications of what they're saying will happen in the future, all of a sudden it becomes way more science fiction than you really want it to be, and then life was sad. And I really should burn that book because it was depressing in every way. So we can't really know the microstate. What we can know is the macrostate, which is the stuff we can observe, like temperature. We can measure the number of moles of gas. We can look at the volume and the pressure. All of those state variables are things we can measure. So we could say we can know this. Here's the thing. The overall assumption is that for every macrostate, so we have a gas at a certain pressure, certain volume, certain temperature, we could perhaps imagine a bunch of different microstates, a bunch of configurations of individual molecules that'll give me the exact same temperature. One case of that would be like, let's just imagine the gas had 4 molecules, right? It's like, well, if a temperature happens because 3 of them are at this velocity and 1 is at this velocity, well, maybe it's just a different 3 of them are at that given velocity that's producing the temperature, okay? So you can imagine a bunch of different configurations of microstates can give rise to the same macrostate. We can see this in an example by not looking at 4 gas molecules, but if we just had 4 coins, 4 coins, pull them out of your pocket, toss them on the table, see what happens. In this particular analogy, the macro state is looking at the system as a whole and just saying, how many heads and tails do I have, right? What is the state of the overall system? Is it 4 heads? Is it 4 tails? Is it 3 and 1? Is it 2 and 2? You can see all those possibilities listed there on the left, okay? In the middle, we have microstates. Microstates would be looking at every individual coin and being like, heads or tails. Pick up another one, heads or tails. Pick up another one, heads or tails. Pick up the other one, heads or tails, okay? So you can see that for 4 heads or 4 tails, well, there's only one possible microstate that corresponds to the macro state of all heads or all tails, right? There's only one option that's there. But as I start to mix them a little bit, for instance, 3 heads and 1 tail, notice, well, we could have these 3 as heads, or we could just change the 3 that are heads and get 4 different possible states. Good so far? You see what's happening there. If we go to 2 and 2, well, I can mix it a bunch of different ways, 6 times this time, to get the exact same macro state of 2 heads and 2 tails, okay? So it turns out that when we just toss the coins in the air, all of these microstates are equally possible. Like, we don't know what's going to happen, okay? Any one of them could occur, but the macrostates have different likelihoods based on the number of microstates, okay? So take a look at what we have here. What is the sum of those numbers? Looks like 16. Notice that 6 of the 16 possible microstates corresponds to 2 heads and 2 tails. Therefore, it's the most likely macrostate to get if we just toss 4 coins in the air, okay? So the relative probability is given by the number of microstates for each macrostate. Are we clear so far? You're thinking, like, what does this have to do with anything? Yes. We're getting there. 1 second. We'll get to the gases or the molecules of gas. Okay? So this is just with 4 coins. What happens, and I wish I was like prepared for a demo with this. We went to 100 coins. What does this look like if we went to 100 coins? And it would also just be fantastic if I had 4 coins in one pocket and 100 in the other, and I just went blah. And then we all just looked at all the microstates and figured out what macro state we ended up in. But we're not going to do that. And also, just looking at these numbers, there's a lot more options all of a sudden, okay? So, again, it works out that there's just one microstate where it's all heads or all tails, okay? There's only one option. But as soon as I start mixing them, well, just imagine mixing in 1 tail out of all of it. Well, any of the 100 coins could be the 1 tail, which means all of a sudden I've got 100 different microstates that correspond to that one macrostate, all right? As we mix them more and more, though, look at these numbers. They start to get a little ridiculous, don't you think? Yeah, like that's just with 100 possible coins, all right? Notice all of a sudden now there's so many different microstates that correspond to the different macrostates such that these endpoints become highly unlikely. It turns out that more than likely you're going to end up somewhere in the middle, okay? With one toss of 100 coins, it's much more likely that you're going to end up with somewhere roughly in the middle as opposed to toward one of the ends, okay? And you can see those probabilities are a little bit ridiculous. You're going to have to toss the coins a lot of times to increase your likelihood that you might get one of the all heads or 1 tails. I think we kind of understand that that's true. So notice here at the bottom, what we're seeing that even by increasing to 100 different objects, the most orderly cases are those endpoints. Orderly would be like, ooh, look, they're all heads, or ooh, they're all tails. Disorderly are the ones in the middle, where it's just sort of a mixing. So we're having the most orderly cases become very unlikely, and the disorderly cases becoming much, much more likely. So what happens if we go to the air molecules in a room? But keep in mind, there's about, 6 times 10 to the 23rd molecules in a mole of gas? How many air molecules are in this room right now? It's not 100. I can tell you that, because if it were, well, we wouldn't look like this, I don't think. We'd all be running around being like, my molecule, and trying to get, like, there's only 99 left. Like, no, I don't think that's going to do us any good. There's way more than 100, so you can imagine these particular numbers are skewing even more toward being much more likely to be somewhere in the disorderly realm and less likely to be orderly. What we mean by that is that the orderly cases, which would be maybe something like this graph, and I don't know why these are upside down, just deal with it, all right? Where maybe I have all the air molecules have decided to just bundle themselves over in this corner and all have the exact same velocity, is probably not going to happen. Okay? We could wait the entire lifespan of the universe, and they're just not spontaneously going to do that. All right? Instead, they're going to be more like the 50-50 heads and tails. They're much more likely to be spread out sort of everywhere in a state of disorder in a bunch of different random directions with velocities that more match the Maxwell distribution. Okay? This is a least orderly case, and it's much, much, much more likely, much more probable. So, based on just this, the fact that we're talking about order and disorder, we're really talking about entropy, and it's pretty clear that just working through those numbers that it's directly connected to probability. Probability, statistics, all of this stuff we've been doing for 4 chapters. Remember at the start, we were talking about micro versus macro and how we couldn't really know all the micro stuff, so we were going to use averages. We were going to use statistical approaches. This starts to show us that the statistical approach is pretty valid because of the tend toward disorder. We're much more likely to end up near those disordered average states, okay? So it has some meaning. So we can add one equation to this whole thing, and for some reason things won't scroll. There we go. That's what we wanted. We can say that states of the most entropy are the most probable, and we have an equation that relates some of this stuff together, and we're not really going to do anything with it. I want you to just be aware of it. The amount of entropy in a system is equal to the Boltzmann constant times the natural log of W. What's W? W is known as the thermodynamic probability. It's sometimes also known as the disorder parameter. And it turns out that this particular thing, let me go above here, is the number of microstates corresponding to the macrostate, which we've already determined relates to the probability of the occurrence of that state. Okay, so this W is a parameter that relates back to kind of like the coins, the number of microstates that correspond to a macrostate and their relative probability of occurring. Again, just be aware of it. If it ends up in the homework, they're going to have to give you W or have you solve for W or something. There's not anything that's terribly difficult there to calculate. So then finally, this whole chapter wraps up with an interesting statement. I don't have the source for this. I'm just told it's been calculated, okay? Just notice this whole idea is all about probability. Like, as someone pointed out, like there is a non-zero possibility that you get all heads or all tails. There is a non-zero probability that for whatever reason, all of us spontaneously suffocate because all the air molecules decide to bunch themselves in this corner. Is that going to happen? No. Is it possible? Technically, yeah. but it's not going to happen, all right? That's just not likely given the, not likely. Not likely is an understatement. It's not likely, okay? So notice, someone calculated what the likelihood was of some of these things happening. So for instance, trying to get order from disorder. See, here we have the idea of a stone that's just sitting on the ground, spontaneously saying, hey, I have energy in the form of thermal energy. Why don't I convert it to mechanical energy and raise myself up in the air? Well, it's not likely, but it's non-zero, okay? So that is apparently much less likely, and I wish I had a number on this, how much less likely than a group of monkeys typing randomly, producing the complete works of Shakespeare, okay? So, again, you're not going to have to worry about the rock picking itself up unless there's a ghost. I don't know what to say about that. Or the air molecules bunching themselves in the room. Don't freak out about these non-zero possibilities, okay? And that is the end of our thermodynamics stuff. Yay! Chapter 20 is done! Whee!